first of all, out of curiosity, from the audience, who knows what three.js is? If you can raise a hand. Okay. Who doesn't know what three.js is? Two. OK. I'm going to do, anyway, a brief introduction for those guys. But then we're going to dive a little bit into technical stuff, but hopefully people are going to be able to follow with all this. So three.js is a library which aims to make the process of 3D content creation for the web much easier. The core is, the way it has been built, the core is not attached to the renderer. So we have the scene graph in one side, some of the utilities, but you can plug any render that you want. You can render that data in whichever way you want. This allows us to have like a WebGL render, Canvas render, SVG render, DOM render, and whichever you want to add another one, it's just up to you. It's obviously written in JavaScript. We have some tools written in Python, which is mainly for like building the library and minifying and compressing and things like that. We also have like a Node.js builder, but we haven't really used it too much ourselves. It's hosted on GitHub, and it's released under the MIT license. So this was, I don't know, you can see it, yeah. This was like a state-of-the-art of Canvas render, like three.js, like 2 years ago. Like we were able to have like a cube with different colors on each face, and with a fake shadow, which is a plane. Even 2 years ago, I think Canvas on its own, like the Canvas API, didn't really have anything. Like no one had really done much stuff with it. So even with this simple cube, like people were like impressed with it for some reason. Like in the past or something. Shortly after we had I had that thing, that cube spinning. We started doing this project, the Wilderness Downtown, that it served like a excuse for like improving the Canvas render a lot. Like we had to add a lot of features to it, even if in the actual music video that we did. We didn't use it that much. We only used it for like some birds on the homepage and some trees on some parts. But it was really, really useful. Like it was really like a Kickstarter for the Canvas render. Like we had like so many features thanks to this. In the same way, we did this. I think it was 6 months after that. We worked on this another music video that, in the same way, it served as a good excuse for like implementing lots of features to the WebGL render. And this is more or less how it is where we are now. Just this is some notes about this graph on the top. This is the graph of commits on GitHub. And as you can see, this was more or less April 2010 when I put it on GitHub. You can see more or less my enthusiasm, how it was going down a little bit. But I think this is more or less when we were working on the Wilderness Downtown website, and then there's a gap, which is, you finish a project and then you are tired for like maybe some weeks. And then this is when AlteredQualia joined in and started to submit some commits. And it created like an interesting phenomenon that we somehow found ourselves like fighting to see who was committing most on to the library. And it kind of, from then on, we had the same pattern that it was more or less here. Like we were working on this wrong website, and then we did the first, like the base code, and we did more features, and then another gap, which is like another project. And then from then on, it's like more random. From then on, it's like community-driven kind of development. Like it doesn't really depend on us. Like it's just more like people, whatever they come in and they just put some comments, and then we just try to see where we're going to go with this. So up until now, there are like about 140 contributors, about 4,000 commits, 55,000 lines of code. The library minified is about 400 kilobytes, and gzipped is about 100 kilobytes, which is something I somehow care about. I always want to, I thought it was like a good limit to have as a gzip library to don't go higher than 100 kilobytes, but we keep fighting, and we are all the time like 95, 99, and it's somehow interesting, but we'll see how it goes. It features really, really, really bad documentation. This is the first complaint from everyone that comes in. It also, like, from time to time, we get some classical developers that come in and say, like, oh, I'm surprised that you guys don't have any unit tests at all. And this is because we have, like, at this point, we have about 175 examples. Those examples really serve as a kind of unit tests, like whenever we change a feature, we improve a feature, we just check those examples that are relevant that are using that feature, and we see if we're breaking something. And at the same time, those examples, we keep them updated all the time, like even in the dev channel, in the dev branch. They are all the time updated, so if you want to learn how something is done, you only have to go to the examples and see how the code is. We also make sure that the repository doesn't have any dependencies. So you can just download the whole repository and you can start hacking around. You can just play with all this. But you need to bear in mind that if you are like, at least if you're using Chrome, you need to execute Chrome with the allow file access from files in order to be able to see some of the demos, because it loads 3D images with JSON or other formats. If you had any questions or you play with that, there is also, we recently moved all the questions from the GitHub. We moved them to Stack Overflow, and so far it seems like some people is helping a lot on that. Like there's some people that try to help the people whenever they have some problems. Also, we have a three.js RC channel on Freenode. So this is how the API is currently. I'm not going to dive like detail the whole thing, but as a part of the reason that we don't have like a good documentation is because we have been like moving a little bit the API. We have just renaming some things, and it's also laziness, but it takes some time to change the API and also update the documentation. And we don't want to put comments on. Let's not talk about that. And okay, so this is how you create a camera nowadays. We have mainly two cameras, like a perspective camera and orthographical cameras, so different kind of transformations of the view. Then you create like a scene, which is where you're going to be like, you can just think about it in a film way. It's just a scene where you're going to be putting all the stuff. On there, we create like a cute geometry. We load the texture. We have some utilities for like this. Will do all the HHR loading and everything on new image loading and everything. And it will then we use that texture, which is just pretty much like a GIF, like just any kind of image that you can load in any website. And we create a material using that texture, and we then create like a mesh that was going to use the geometry that we created with the cube, with the material, and we add that to the scene. Because we're using this foam material, if we don't have any light in the scene, we are not going to see it. So we need to put the light in the scene. And in this case, we are copying the position from the camera into the light. So it's going to look like you're pointing a light into what you're seeing. And then finally, we create a render. In this case, we're creating a WebGL render, which we're enabling anti-alias, so it looks much nicer. And the only connection to the DOM in this case is just like every render has a DOM element inside, which is just like a canvas. And you can add that as a pen child of any node or any part on the DOM. You can also pass a canvas that you already created to the constructor, but this is the usual way that we usually do it. And then for animating, we recommend using request animation frame. And in this case, we're just changing the rotation on the X and the Y axis. And every frame, after that, we are just rendering that scene from that camera. So we end up with this super amazing cube, a super amazing crate. And just so you kind of see what's the difference with all this, like I'm the first one that I like really like a big fan of vanilla.js. But if you want to see what's the code for doing this cube crate with WebGL, like use vanilla.js, it's something like that. Like you create all these uniforms, you create all this painting the texture. I think down there's the cube. Like here you define all the vertices. A bit more, all the drawing stuff. And this is even considering that code is already using some utilities for doing all the render. So next thing is just show a little bit some of the things that we have been working for the last year or so.
Thank you. So here is a scene that we would be able to render with a WebGL renderer from some time ago, maybe a year ago. And it looks pretty decent. There are 3 dynamic lights, fog illumination, specular highlights, environment mapping. But the question is, can we do better? Like a lot of times people when they see WebGL demos, they are telling it's looking like rendering from the 80s or from the 90s. And the answer is yes, of course. We can look to the eternal inspiration for the advancement of the computer graphics, which are computer games. So we use some techniques from the computer game developers, such as using gamma-corrected rendering pipeline, replacing ad hoc shading models with more physically based rendering, or for example, using nice-looking but cheap to render approximation of the subsurface scattering, for example, used in Half-Life 2 by using wraparound lighting. Here is how this thing can look when we use exactly the same scene, but we are using more advanced rendering models. It's running at 60 frames per second. It's looking much more realistic. Now, if you play games, a lot of times people are complaining that textures are not looking okay, and often the trouble is not the quality of the images, but it's how the textures are being interpreted on the graphics card. People are complaining that textures are looking blurry. Here, how we can improve this? Fortunately, WebGL standard has a mechanism to how to be getting newer features via WebGL extensions. And here we try to evolve our renderer to be incorporating new features that are available in the WebGL as soon as they become practical to be used. So for example, anisotropic filtering for having nicer and crisper textures just recently landed in the stable browsers. So we modified our texture uploading algorithm to be able to use anisotropic filtering. Here, for example, you can see on the right side is the old way of using trilinear filtering. When if you check how is the texture changing closer to the horizon, there is getting blurriness. Well, if you use anisotropic filtering, the texture stays sharp. Exactly the same image, but it looks much better when we use more advanced filtering. Now, another way how to be getting higher visual quality of the rendered images is to be adding more surface details. And here we take advantage of another of the WebGL extension that was coming quite recently to the stable browser, is to be using standard derivatives extensions, which allow us to be doing high quality map mapping. This is example like what we have been able to do, like state of the art of three.js rendering 1.5 years ago. With both me and Mr. Doob, we have been trying to make it look as good as possible, and that's what we have been able to do. But with more modern techniques, that's what we are able to achieve in the browser, running at 60 frames per second, very high detailed. What else? So it's exactly the same model, just we use more advanced techniques, and also browsers have been catching up and they've been adding more features, so you just have to wait and future will come. Now, it's important to be able not to be having images that look nice, but also we want to be running as fast as possible. And if we already have a WebGL that is running directly on the graphics card, we are able to take the advantage of hardware acceleration, not just for the computation of the shading, but also we can try to offload computation of the simulations to the graphics card. And here we use another of the recent features where we are able to pass floating point textures, which we can use to pass the data to the graphics card in an efficient way. So for example, it's useful for particle simulations where if we have been doing particle simulation just on the JavaScript, we have been able to have like tens of thousands of particles. Here with floating point textures, we can have 1 million particles running on the GPU. CPU is almost quiet. It's just put the shaders on the GPU and then everything is done in the graphics card. Another simulation that we can offload to the graphics card is animation of the characters. So for example, we are having hardware accelerated skinning, where either we can be having like a lot of very simple characters. It's about 400 buffaloes, which are animated entirely on the GPU, or we can try to have less, but much higher quality characters with high details, which you're probably familiar from. It's again rendered at the 60 frames per second running in your browser. Now it's important not to be having nice images and running fast, but if you want to be doing more complicated applications, you are going to want to be putting more and more data inside. So for example, when we have been starting, we have been doing almost everything was having a representation of our models in the JavaScript, down to the things like every vertex was JavaScript object, but we soon found out that this takes really a lot of memory. So we tried to be using more efficient memory representation of the geometries. And for example, we are using just typed arrays that we initialize from the JavaScript. But once we upload it to the GPU, then we can just completely forget about the JavaScript part. And then we are able to get crazy savings on the memory, both on the memory and on the initialization time of the models. Here is an example of 160,000 geometries that it initializes instantly, and it's also running fast because the layout in the memory is more friendly for the graphics card. Now, a big part of the models is not just the geometries, but also the textures. If you are doing classical web developments, you are mostly concerned with the sizes of the textures which are going over the wire. But if you are doing 3D graphics programming, no matter how small is your JPEG or PNG on GIF, it's going to be expanded to the full-sized image on the graphics card memory, and very soon you are going to be running out of the GPU memory. So for this, game industry developed compressed textures which are uploaded compressed to the graphics card, but then they are uncompressed directly just in the time when they are going to be used for the rendering. So for this, we have just very recently implementing support for compressed textures. We don't have yet any nice, beautiful demo, but you can get quite a large savings on the GPU memory cards, which means that in the future you'll be able to put more rich virtual worlds on the WebGL applications. Now it's important not just the sizes that are being in the runtime, but it's also important the sizes of the models that are going over the internet. If you check modern games, even simple indie games are like hundreds megabytes to gigabytes. So if you are used to the web that you click on something and it's immediately available, it wouldn't work if we would have too large sizes of the models. And here we have been trying various approaches where we started from the simple JSONs, and here we have been quite lucky because the whole web stack is made to be working with the gzip. So we never actually have to be looking on the side of the uncompressed model, because anyway, if you are saying you are going to be using gzip for transferring all your data, but even here, if we are using the data formats that are knowing about what's inside the data, we know that these are vertices, and we can truncate some of the precision, and it's still going to be looking okay, and we are able to get like 5 times smaller gzip sizes. Here is, for example, this is a model that we have been speaking about, and it's a high detailed model that itself is similarly sized, like if you would have one PNG just with a screenshot of the image. And for example, this is a fairly detailed model that both geometry and the textures, we have a back illumination. This is 700 kilobytes, and you see that it loads instantly. And here, Ricardo will tell about what's next in the pipeline.
So most of those things that he has been talking about, those things are already like on the library. You can use that. It's not something that works magically, but you have calls, or you have API to use all this stuff. Some of the things that we have been experimenting with has been like more renders. Like there is people that still rely on canvas render because WebGL still doesn't work on Internet Explorer. It still doesn't work on, like, Safari is not enabled by default, or like iOS, it doesn't work at all. So those people still want to have some 3D graphics on the web. So they use the canvas render, and the problem with the canvas render is it just is a hack on top of each other. Like for doing like many things, like we do like really crazy things that you will be laughing for days. The problem with that is that, for instance, the Canvas API, the Canvas Vector API, has anti-alias enabled by default, and there is no way to disable that. That creates problems like when you draw true polygons, you will see like a line in between it, like if it was wireframe. A solution for that, what we do is just expand each polygon like a little bit so they overlapped. So I was talking with some of the people that kind of define that kind of spec. Like we'll see if it was possible to reuse like the WebGL spec in the same way that you can enable or disable ActionScript, but they just told me like, oh, what's the use case? And I was showing like, oh, I just want to have this 3D stuff, and they told me, oh, you use WebGL for that. Okay, so at that point I was like, okay, so what's the solution, or what kind of things can we try? Like at that point I was wondering, like, is it possible to, what would happen if we still use the Canvas render, but we still Canvas API, but we don't use the Vector API. We use like the image data API. So you get a buffer, you get like a type array, which is just like all the pixels in the buffer. And you draw the triangles pixel by pixel. Like, you know, it sounds crazy, but this is how the 3D was done 20 years ago. So, I was just curious to see how it was going to be, and how it was going to be performant or not. So the output is not exactly the same, because I haven't, the problem with this kind of render is that it takes some time to implement the features. But this is how it was, the kind of thing that you can do with Canvas render, like in this case, I don't know, you can see, we wait for the light. Cool. So in this case, it's technically the same thing as in the other demo, even if they look different. We're just creating triangles, and we're doing a crazy bitmap and drawing 3 pixels, and then somehow scaling that, and we're using that as for like painting each triangle with different colors on each corner. And this is, 6 frames per second, and in this machine, which is pretty powerful. Sorry. And this on an iPad, this is about 1 frame per second. So what we have now is just this one, which is, the technique is the same thing. It just, again, doesn't look the same, but the bottleneck is not on calculating the light. The bottleneck is on rendering those triangles. And we can see that this one is 60 frames per second, which is quite an improvement. The problem with this is that we cannot, well, we can do anti-alias in the long term, but I won't want to try to do that. But the thing is, on an iPad, the previous one, as I said, it was 1 frame per second, and this goes at like about 10 frames per second. It's still not good enough, like it just 10 frames per second, but at least it's just whole or something that maybe they improve the type performance, and we'll see where it goes. But at least we have some options. This is, of course, this is not something that really I can make it that fast. Like I'm lucky that a German guy called, a demo scene guy called Rick helped a lot to make this the way the render is done. And also there is a Slava, like Yegorov, that helped on making that it didn't, like to make it that, like double check the codes to make it that, to make sure that it was running fast. So we're going to be developing this a little bit, and then hopefully at some point we'll be able to have like a render that is as full feature as the Canvas render, and then you have an option. But so far this is all we have right now. Then another renderer, if we didn't have enough, is the CSS 3D renderer, which I don't know if any of you have played with the CSS 3D, but it's a little bit like kind of WebGL in a way. You have to do all your matrices, nested matrices, all the transformations and rotations, and it can be a little bit like cumbersome. So at some point, I was wondering what it will happen if what I was doing in render with three.js. So you only do the same thing, like you just create a plane and add it in the scene, and then you just move the camera around. So this is what we had so far. So the cool thing of this is that all those are just iframes that are loading like some effects from my website. But as you can see, it's still interactive. So that's something, an instance that even with WebGL you cannot do easily, because you cannot use a website as a texture for on WebGL. But you know, with CSS3D, you can just do these kind of hacks. So it's again, it's really limited. Actually, maybe I can see. I don't know. You can see anything. Like it's just creating this CSS3D, just creating an object that you just add a div into it, and then we do all the the renderer will do all the usual matrices for you. It's really limited to whatever you can do with divs. But you know, there is still like the Circle du Soleil demo that we saw some months ago from Google, that you can do this kind of stuff, but without having to deal with CSS3D syntax. You can just move the camera around without having to think about it. And so far, for the last 2 years, we have been doing a lot of work, like kind of creating resources and doing a lot of code that basically makes the developers happy. But we had all the artists on the side, like without being able to do anything, because the artists won't be able to play with all these unless they learn to code. So for the last some months, we have started doing an editor for all this. So straight away, one of the main benefit of this is that what you see here, this is, let's see if I can. What you see here, this is already the WebGL render. So you can already preview how your model is going to look in this thing. So for instance, let's see. We can load any model that all the formats that we support. Like we have like an OBJ loader, we have like a Collada loader. You can just drag and drop them, and then we can load as much as we can. And here you can start playing with the usual kind of API in a visual way, like the three.js API. So in instance, we can load the color. We can use font material. We can increase the specular light, which of course it doesn't look too realistic. But we have this specular map, which does all the magic for us here. And now we have something which, you know, it will look at the head, it looks a little bit more realistic. And I think we have, was it bump or normal?
Bump, yeah.
Bump. This one. We enable it. You know, you can still like tweak more or less how you want it to look. And let's see, something like this. Oh. Like this and like this. The thing of those color pickers is that on Windows they are not real time, but on OS X and Chrome OS they are real time. So you can just change the color and you see it on the model in real time. But I guess at some point we'll just do our own widgets, so this works in any platform. So the good thing of this is that the artist can just come here, just tweak all those. You know, it's like Unity 3D kind of thing. Just load up the models, put all the materials and all the you know, just to really see control how he wants it to look. And then we still had to add this, like then you will be able to export this, or you can just compose the scene and you export this for the programmer, and the programmer is just gonna be like a JSON that he just needs to load, and it's gonna look exactly like the artist wanted. And what else this has? Oh yeah, and of course this is right into the three.js repository. So this means that this is also MIT license. So it will be like interesting. Like this I can see this being as a good base for someone if someone wants to build like a game, they are building a game and they want to have like a level editor. They can just hack around the tool and do the panels that they want to do or whatever they want to do. And at the same time, if someone wants to add a panel at the bottom so they can use how to encode editor that executes some, you can just hack whatever you want and add some scene to the, some objects to the scene. You can just start creating like procedural scenes, and you can just play with it visually with what you are creating. And yeah, we think it has a lot of potential, and we really are curious to see how, you know, we're in the same way, like in the same way that we built like three.js, we were not sure. I mean, we built it because we needed it, But then people come in and they say, oh, what about having this? Like, oh, actually, that's interesting. But the same thing here. Like, we're just building because we think it's something that we need. And we'll see how people evolve it, like how people, what they suggest and how the whole thing evolves. So with that over, that's it. Thank you very much.
Do we have any questions? Oh my gosh, why'd you have to be over there?
Because you said at the beginning that the whole library is about 400K, right?
The minified build.
Okay, but can we like build it without, for example, Canvas and DOM renderer, only WebGL stuff, and it will be smaller?
Yeah, if you go to the, well, there's a folder called Tools, where we have the Python build, and it includes some JSON files that you can just run the builder using any of those JSON files. And those JSON files are just the files, the list of files that you want to include. There's some trickery of some of the, when you're doing the list, which one goes first, but you can just try.
Thank you.
No problem.
Anyone else? Oh man, my mind is blown. Thank you guys so much.
For sure.